Hello everyone, today we are going to talk about group theory. First of all, you may notice my new setup here. I've changed my setup because with my iPad, the Apple Pen made some annoying sounds on the device. So with this new setup, hopefully, the only annoying sound you hear is my voice. So let's start. So a group is a set that has some binary operation that satisfies these four properties. Now, a binary operation is just an operation that has one element operated by some other element, right? That's what it means. So, like A times B, multiplication is a binary operation. So, a set has some operation that satisfies these four axioms. And if those axioms are obeyed, then the set is called a group. Now, let's kind of dissect this. So, first of all, what is a set? Now, I strongly advise you guys to watch my last video if you don't know what a set is. But a set is basically just a collection of objects. So I may have some sets. Let's call this set S. And S is just some collection of objects A, B, and C. Now this is kind of boring, uninteresting, because we just have some set that has a couple of elements, and that's it. We just have some group of A, B's, and C's. Sorry, we have some sets of A, B, and C's, and that's not fun. Now we could make this set a bit more interesting if we had some operation on it, like addition. So if we have some notion of addition on this set, we can now add elements in this set, get some other value. You can add B and C, you can add C and A and stuff. We have some operation here that we can impose on the elements of the set. So what we have done by defining an operation is we have kind of expanded our workroom here to deal with the values of the elements of the set itself. Something that isn't covered in set theory. So group theory is much more general because now we can talk about operations acting on the elements of the set. So group theory. So this is actually not an example of a group. I just gave you this to make you have some notion of what a group is. There's a bit more to groups than just an operation, and that's where these axioms come in. So a group has to be a set that has some binary operation that satisfies these four properties. So it has to be closed under the operation. So what does that mean? Well, being closed under the operation means that, well, let's actually write this down. So say I have a group, let's call this G. G is my group. And let's say that A and F are elements of this group G. So G, so an operation is closed. An operation. So a set is closed under an operation if A operated with F is also in the group. So a group is closed under some operation if we take any two elements of that group, apply that operation, and the result is also in that group. So it also has to be associative. So what does that mean? So say I have A operated with F operated with K, and that equals some value, all right? If we evaluate these ones first, so if we do A operated with F, then operated with K, and we do A operated with F operated with K, but we evaluate F and K first to get some value, these should be equivalent. So it shouldn't matter which part we evaluate first, our result should be the same. That's just axiom 2. 4 minutes already, wow. Axiom 3, there exists some identity element E such that A operated with E returns A for all A is in G, which means that for all elements of G. So what does that mean? It means that, say I have A, right? A is an element of G, and I operate A with the identity elements. I should just get A as a result. That's what it means. If I operate with some number, there should exist some number, or A operated with that number returns A. Oops. For all A, for all members of the set, even for E, operator with itself should equal E. So E has to be in the set, by the way. Okay. Third or fourth, there exists some B that's in G where A, B equals E for all A's in G. This means that I have I have A and I have some B, and I get the identity elements. So this is actually called so B is called an inverse operation. Okay, and if these 4 rules are obeyed, we have a group. So let's give some concrete examples of groups. So the integers is an integer a group. So an integer, we just have 0, 1, 2, 3, and so on. All right. Now, sorry, our integers or group doesn't really make any sense. So our integers a group under addition. So let's let our operation be addition. Also, previously I used this circle plus sign to represent a general operation. So are the integers are they a group under addition? Let's test that out. Well, is it closed under the operations? Is it closed under addition? Well, 1 plus 2 equals 3, and 3 is an integer. 0 minus 1 equals minus 1, which is an integer. 8 plus 3 is 11, which is an integer. If we take any of these elements and we add it to any of the other elements, we will get a member of the set. So yes, it is indeed closed under the operation. Is it associative? Well, say you have 1 plus 4 plus 3. It doesn't matter if I evaluate 1 plus 4 or 4 plus 3 first, we will get the same answer, that being 8. So it is indeed associative. The operation is associative. Does there exist some identity element inside a thing? Well, yes. So does there exist some elements, for example, where 1 plus E is 1? Well, yes. That element is 0, and 0 is in the set, as you see over here. So 0 would be our identity element. So 3 is obeyed. 3 is obeyed. 4, does there exist some B where A equals E? So does there exist some number where 5 plus some B equals the identity element 0? Oh yes, that being minus 5 for this case, which is actually in the set, because you have plus and minus, all of these things. So the inverse of any elements would just be minus that element. So if A is some general element and Z minus A would be B. That would be the inverse. Okay, and fourth, yeah, that's it. So yeah, the set of integers under addition is an example of a group. So what's an example of something that's not a group? Well, you can use this integer set again. So let's have the integers, plus and minus, 0, 1, 2, and so on. But let's bring this a bit more down. Okay, let's actually use this. Okay. So here I have the integers, plus, minus, 0, 1, 2, 3, and so on. But let's let our operation be instead subtraction. Okay, so is the integers under subtraction a group? Well, it has to be closed under the operation. Sorry, not subtraction. I meant division. Is the integers closed under division? Okay, that's what the example I'm going to use. So is it closed under division? Well, if I divide 1 and 2, I don't get something that's an integer. I get 1/2. That's not an integer. So already we see that it doesn't obey 1. It has to obey all these 4 things, but it doesn't obey 1. So also, if we divide 1 by 0, we get a number that's not in the integers. Typically speaking, it's undefined. Now, to be a bit more exact here, we can define 1 over 0. That can be, technically speaking, we'd actually have to define division, which we haven't done at all. But with the intuitive notion of division, 1 over 0 is undefined, like under the field axioms. However, if we expand our axioms to the real algebra, 1 over 0 can be defined as a nullity, but that's a story for next time. But 1 over 0 isn't an integer, even in that realm of axioms. It's not an integer, so it's not closed under the operation. But is it associative? Well, is 1 divided by 2 divided by 3? It doesn't matter where you put or what we evaluate first. Well, let's see. What's 1 divided by 2, then divided by 3? That's just saying 1/2 times 1 over 3, which is just 1 over 6. Well, what about if you evaluate, if you do 1 divided by 2 divided by 3? Well, 2 divided by 3 is 2/3. 1 divided by that, that's just keep, change, flip, and we get 3 over 2. Of course, 1 over 6 is not 3 over 2, so it's not associative either. However, does there exist some identity element? Well, let's see. So a divided by something should return a. Well, that's just 1, right? Since 5 divided by 1 is 5, 0 divided by 1 is 0. Our identity element would, just like for addition, actually not for addition, but our identity element would be 1. Is there some inverse? Well, does there exist some b where a divided by b gives us 1? Well, yeah, b would just have to be 1 over a. Do the algebra to find this. If a over b equals 1, b of course would have to be 1 over a. That would be b. Okay, so yeah, so there is an inverse element 1 over a. Like for example, for 3, the inverse will be 1 over 3. Sorry. I was thinking of, wait 1 second. Wait. Does there exist, so if I have like 5 or something, 5 divided by, okay. Yeah, I was thinking of multiplication instead, sorry. The inverse isn't 1 over a. So 5 divided by a should give us 1. So 5 over a should give us, does there exist something? Well, yeah, the number itself. So the inverse element would actually be a, which is pretty cool. That would be the inverse, since anything divided by itself gives us 1, and 1 is our identity element. Okay, and yeah, so 3 and 4 are obeyed, but not 1 and 2. So therefore, so that means that the integers under division is not defined. So yeah, that's an example of something that is not a group. Now here's a little extra that I also want to introduce a bit. There are types of groups as well, and there is one type of group that I want to talk about briefly, that being Abelian groups. So if we have a group where the elements commute under the operation, that group is called an Abelian group. Again, this does not have to be obeyed to be a group, but to be an Abelian group, it's defined that the operations have to commute. So, for example, for the integers under addition, which is right over, where did I do that? Integers under addition. I don't know where that went, but the integers under addition, plus minus, 0, 1, 2, 3 under addition, that would be an example of an Abelian group, since 1 plus 2 equals 2 plus 1, a plus b equals B plus A, where A and B are just members of this abelian of this group. Okay. An example of something that is non-abelian, where the elements don't commute, is well, to be an non-abelian group, these have to be obeyed, and 5. So the integers under division cannot be non-abelian because since it's not a group in the first place. So we could explore some examples of groups that aren't abelian, groups that don't commute. I think an example of that could be the cross product with vectors, since some vector cross product some other vector may not be the same thing unless like one of those are the null vector. Since this would pick up my minus sign, they actually anti-commute. Another example, if you saw my space-time algebra video, an example of groups that don't commute would be the gamma matrices. Since this gamma mu would be minus gamma mu for mu just not equal to nu. So they'd actually anti-commute, and they do form they are a group, since where if the operation is well, I guess you could say the dot product or something, the multiplication operator. So yeah, the space-time algebra is an example of a non-abelian group. And so yeah, also I believe the cross product of vectors. So yeah, that's an intro to group theory. If you guys want to see more about group theory, please let me know in the comments below. If you like this new format, you want me to continue this format, please also let me know. But yeah, that is group theory. Have a great day. Bye.